Here are sample calculations using sample data from the lab. For the circumference, you would take 2 times pi times r. So 2 times pi, you can round pi to 3.14 or use the pi key on your calculator, and then you would use the radius from each trial. Multiply it all together. Remember, this is the distance around the whole circular path. So it's in meters. Circumference is in meters. To calculate the velocity, we're going to take circumference divided by period. We want to know the distance divided by the amount of time, meters per second. So I'm going to take 16.14, so the circumference, so whatever circumference you got for trial 1, divided by the time you got for trial 1. Same thing, take the circumference, the path or the distance of the path that car followed, divided by the time it took to follow that path. Repeat for all of the other trials. Use the circumference from above and the time or period from your lab. Remember, your numbers should not be the same as this. This is just an example of the calculations you'll need to follow. What did you notice about the velocity of the cars? The velocity should remain the same during each trial. Remember, when we talk about velocity, it's the velocity that if we cut the string, how fast that car would keep going straight, tangent to the curve. To calculate the centripetal acceleration, we're going to use the formula v squared divided by r. We know the radius. We know the velocity, so we just calculated it. So you're going to take the velocity from the last set of data that you just calculated and divide it by the radius of each trial, which we have in our chart in our lab. Throw it in your calculator. There you go. Remember, if you have a formula that is a big ratio, so it has a division symbol between the first half and the second half, or the top half, the bottom half, however you want to look at it. Simplify the top, then simplify the bottom. So I would do 0.44 squared, get that as a decimal, and then divide by 1.83. For calculating the centripetal acceleration using this formula, we're going to test it out. We're going to take 4 pi squared, remember pi is 3.14, or you can use your pi key on your calculator. We have the radius from each trial. We have the period from each trial. We got these both in our labs, so we can multiply it together. You should get the same value. Remember, these are just example calculations. These are not the same numbers that you should get. It should be very much based on the data you calculated for your period, the data you set up for your radius, which was your independent variable. When we use either formula, we should get the same exact acceleration. It's the same motion, so it doesn't matter if I'm looking at the period versus the frequency. As long as I'm using the right formula, I should be able to get the right acceleration. What happens to the acceleration as the radius decreases? We started to see that it increases. They are inversely proportional. So as the acceleration goes down, the radius increases. As the radius decreases, the acceleration increases. How can an object that's moving at a constant velocity be accelerating? Remember, if we cut that string, that car would drive off tangent to the curve at a constant velocity. However, it's constantly changing directions. Changing directions is one of the 3 types of motions we see in acceleration. Acceleration can speed up, slow down, and change directions.